Okay, so first thing we want to talk about is, what is a matrix? A matrix is a rectangular array of numbers in rows and columns. Okay. So it's not just numbers anywhere, it's numbers organized in rows and columns. Every matrix has an order. Another way to think about order is the word dimension. Order names the number of rows by columns, and we abbreviate rows and columns M and N respectively. So we name the order M by N. This would be a great thing to take away from today's notes, like what's something I really need to know for the remainder of Chapter 8 to help me be successful on that test next Friday. I have to remember rows by columns. Rows by columns, rows by columns. So that you don't accidentally start doing columns by rows. I don't even want to say it out loud. Okay, but know what order is. An entry for a matrix is any number in a given row and column. So the entries are the specific numbers in the matrix. There is a special notation for naming a particular entry, and it looks like A sub ij, where I is the row and J is the column. Again, it always goes in the order rows by columns. Rows by columns. If anybody in here has had experiences with sequences and series, this might seem kind of familiar in the way that you name a term in a sequence. So if I see something A sub 3, 2, if I was working in another chapter or working in another topic of sequences, I might see that as the 32nd term of a sequence. But because I'm working in the matrix, I would see that as the entry in the third row, second column. Okay. Next up, we want to talk about the order of the matrix. So remember, order is rows by columns. My first example is a matrix with 2 as an entry. What is the order of that matrix? How many rows? 1. How many columns? 1. So my order is 1 by 1. How many rows? Rows. Rows. 1. How many columns? 4. So rows are horizontal, columns are vertical. So thinking about order, this is a 1 by 4. This matrix also has like a special kind of category. Because it has only one row, it's called a row matrix. If a row matrix exists, what else do you suppose exists? A column matrix. Give me an example of an order for a column matrix. 4 by 1, 5 by 1, 2 by 1, right? Next matrix. I want you to just look to the people in your small group. Tell them the order of this matrix on the board. Order should be 2 by 2. This matrix also has a special name. It's called a square matrix. Anytime you have the same number of rows and columns, it would be square. So 5 by 5, 20 by 20 is square matrices. Okay. And the last one, look at your group members and tell them, what is the order of this matrix on the board? Tell them the order. Count your rows, 1, 2, 3. By your columns, 1, 2. Should have said 3 by 2. We okay with this? Yeah. Now, order is going to be really important in another section when we start doing matrix operations, adding, subtracting, multiplying. Okay, so keep that in mind that the order is important at some point, and it's always rows by columns. Okay? Okay, moving right along, we're going to talk about something called an augmented matrix. An augmented matrix is a matrix derived from a system of linear equations. Oops, spelled equations wrong. Derived from a system of linear equations. Now, when we do augmented matrices, when we change that system, we want all the equations in the system to be in the standard form of the line. Okay, so ax plus by equals c is considered standard form. We have all your variables on one side of your equation, constant on the other side. Okay, so if you were going to write a system that had lines in slope-intercept form, change them into standard form first. Okay, so get x and y on the same side, get your constant on the other side. So only work from standard form. And then here's an example of a 3-variable system. I'll read the 3 equations. If you want to jot them down in your notes, you can. X minus 4y plus 3z equals 5. Negative x plus 3y minus z equals negative 3. And 2x minus 4z equals 6. And we're going to change that into an augmented matrix, and I'm going to show you what the augmented matrix looks like. Remember, that augmented matrix is derived from the linear system. Tell me, what's different about the matrix compared to the system? What changes? Oh, Nick says very quietly, they took out the letters. Okay, so that's important. In a matrix, remember, it's this rectangular arrangement of numbers in rows and columns. So the rows and columns, kind of like an Excel sheet, serve as your labels. So I could label this very first column as like an x column. It's all the coefficients to the x terms. 1, negative 1, 2. The second column would be my y column. Okay? And the third column would be my z column. If you were thinking about naming your rows, remember how like when I solve systems in section 7.3, I would label them A, B, C. So you have your columns X, Y, Z, then you have your rows A, B, C, and an entry would be like the y coefficient in the equation B, thinking about like your entries there. What else is different or kind of new to us? Emily? Okay. Oh, yeah. What's different? Those dots. They use 3. And I don't even know what kind of symbol you would call that. When I write out an augmented matrix, I just use a colon. So I use 2 dots. Okay. So the colon is really going to replace what in the equation? The equal sign, right? So we just know like that's where we have something equal, and then we've got these constants on the other side. Okay. Now, that's the augmented matrix. Please note that there is something called a coefficient matrix. If you were ever asked to write a coefficient matrix, and we'll do this later this week, the coefficient matrix would really only be the numbers that are coefficients to the letters x, y, z. So notice the augmented matrix has those colons and then the constants that each equation is equal to. In a coefficient matrix, you would not include those constants. You would not include the colons. Okay, so that piece would be missing. Okay, strictly coefficients to the variables. Okay, so So could you please write out the augmented matrix? I'll read the system again if you want to write it down into your notebook, or you could write page 547, number 20, if you want, and you don't want to write out the whole system. The first equation is negative x minus 8y plus 5z equals 8. Second equation, negative 7x minus 15z equals negative 38. And the last equation, 3x minus y plus 8z equals 20. Could you please write the augmented matrix for that system of equations? So think about what changes from a system of equations to its augmented matrix. Does your augmented matrix look something like mine? Keep these there. Make sure that you have a 0 in the second row, second column for the coefficient for y in the second equation. There was no y. So remember we talked about in chapter 7, like some people don't like how the book leaves that space. Now some of us might be able to say like, oh, I see why they're leaving the space so everything lines up like it would be in a matrix, right? All the z's are in a column. All the x's are in a column. So then you have that 0 there. You should also be able to go backwards. Okay, so my next example is going to ask you to write the system given the augmented matrix. So if I give you an augmented matrix, can you tell me what the linear system was? Now, in the textbook, it will say use x, y, z, w. That just depends on what the augmented matrix looks like. If it looks like our previous example, I could see that I have 3 equations in 3 variables. So I would use x, y, z. If I saw 4 equations in 4 variables, I would use x, y, z, w. Okay. And if you only have 2 equations, use 2 variables, x and y. So could you please write the linear system for this augmented matrix? You're working backwards. And this would be same page 547, number 23, if you're jotting that down. If you're going from augmented to linear, you should be adding back the variables. You should be adding back the equation signs. Something like this. Okay, what are you thinking so far about matrices? Emily gives me a thumbs up. Pretty darn easy, not hard. Okay, good. Okay, now, the last things that we're going to talk about and look at examples for are elementary row operations and something called row echelon form. Okay? So, when we call them elementary row operations, a synonym for elementary here would be basic. They're the basic row operations that you can do. Those bullet points that you're copying down right now, those are the things that are row operations. They are things you are allowed to do to a matrix. You should not do anything other than these 3 operations. Okay, so the first one, interchange 2 equations. That means switch them around. If you've got a first equation and a third equation, you're allowed to switch it. Make the third first, make the first third. And so you can change their order in the matrix however you want. Okay. Number 2, you can multiply by a non-zero constant. You could multiply by 0, but that would not be very exciting. Everything would turn into 0. So you are allowed to multiply the whole matrix or a row of the matrix by a particular constant. That would be kind of like a scalar. Okay. So you're allowed to do that. You can also add a multiple of one equation to another equation. So I could say like multiply the second equation by 3 and then add that to the first equation. So that's totally allowed. Hello. Thank you very much. I appreciate it. Have a good day, guys.
That's amazing.
Okay, come on, Brian. Let's go. Bye, guys. So friendly.
You know that. Come on, let's go.
Okay, so you can add a multiple of an equation to another equation. What's being described right here is basically what you did when you were solving systems of equations in chapter 7, when you do it algebraically, right? Like you just multiply an equation by something and you say, I gotta multiply this equation by -2 so I can cancel out the x's. Okay, that's basically what we're doing in the row operations. Okay, okay. This leads us to something called row echelon form. What is row echelon form? Here are some characteristics. This is how you know a matrix is in row echelon form. After you write these down, I'll draw a visual of what a matrix in row echelon form looks like. If you have a row of all zeros, it's at the bottom of the matrix. Not all matrices in row echelon form have a row of all zeros, but if they did, it would be at the bottom. All the other rows have their first non-zero entry. And so I'm thinking about, okay, I'm in this particular row, and I've got a certain number of columns. The first column that is not 0 in that row is a 1. There could be other numbers after that 1, but the first number is always 1 if it's in row echelon form, if it's not 0. Okay. And for 2 successive rows, the leading one in the higher row is further left than the lower row. So as you go down in your rows, your ones start to move to the right. And I'll draw a picture of what this looks like. Okay, but make sure you get that rule down. This is a matrix in row echelon form. Okay. When I refer back to my characteristics of something in row echelon form, if I have a row of all zeros, it's at the bottom. Check, I had a row of all zeros. Do you always have a row of all zeros? No, but if you do, it's at the bottom of your matrix. Okay. All the other rows have a first entry, non-zero entry of 1. So in the first row, my first entry, non-zero, was 1. And in the second row, I have an entry of 0. That's okay. But the first non-zero entry in that second column is 1. Okay, so 1s have to leave the rows aside from 0. Okay. And then, for that third bullet point, if I have 2 successive non-zero rows, meaning they're not made up of all zeros, like that last one, the leading one in the higher row is farther to the left than the lower row. True. Okay, so this is what I'm saying when as you go down your rows, it looks like your ones are moving to the right. You're getting further over until there aren't any ones at all, and it's all zeros. Does that make sense? Okay, I can have those other numbers behind it, that's totally fine. Okay, but I just need those very first numbers that are not zero to be 1. Okay, and then they'll go in descending order. Okay, next up is something called reduced row echelon form. Okay. Reduced row echelon forms means that there are only zeros and ones. So if any of you have ever worked with binary things, then it looks more like the binary system, only zeros and ones. So zeros are above and below every leading one. So I'll draw some examples of reduced row echelon form. Reduced row echelon. Reduced row echelon. They aren't very exciting. Bless you. Okay, they have all the characteristics of row echelon form, the way the ones move further to the right as you go down the rows, other than the fact that no other numbers are allowed. Okay. So we're going to do an example of row operations. We're going to get an augmented matrix, and then we're going to perform some specified row operations for us. So this is example 4 on page 541. I'll read, when I read the matrix, I'm going to read down the columns, because when I write a matrix, I always write my columns because I want them to be organized. So I'm going to read down the columns if you want to copy it down. 1, negative 1, 2. Negative 2, 3, negative 5. 3, 0, 5. And then you've got your colons. And the final column is 9, negative 4, 17. Okay, now in this example, I'm going to tell you what the steps are. You will, I believe, on your homework, be asked to write it in row echelon form where you pick the steps. Okay, so the idea here is that we're trying to get it to be row echelon form. So we want the first value or the first non-zero entry to be 1 in every row. Okay? So first idea, add the first row to the second row. So which row are we changing, the first row or the second row? We're changing the second row. So that means for this very first step, I can write out the first row. I could write out the third row because I'm not changing those right now. The only row I'm going to change is the second row because I'm going to use the elementary row operation of adding one row to the other row. So right here, I'm going to do r sub 1 plus r sub 2. And I usually, off to the side, keep track of what my row operations are. Otherwise, it'd be really hard for you to tell what you did. Okay. So, what is 1 plus negative 1? 0. What's negative 2 plus 3? 1. What's 3 plus 0? 3, and 9 plus negative 4? 5. So see the benefit of that row operation. By adding row 1 to row 2, I have produced a 0 and then a leading 1. So I'm liking what I have. Now I've really got to concentrate on row 3, right? I'm going to get rid of all those numbers there. So the next thing I'm going to do is I'm going to take negative 2 times the first row and add it to the third row. What am I trying to do when I take negative 2 times the first row and add it to the third row? I'm trying to cancel out those 2, aren't I? So it's like you're doing elimination with a 3-variable system. Okay? So I'm going to make my matrix. Which row am I changing? The third row. To the third row. So I could write the first and second. They're not going to change. When I do elementary row operations, I only change one row at a time. So I'm going to write the first 2 and not change them at all. 1, negative 2, 3, 9. 0, 1, 3, 5. But down here, I'm going to do negative 2 times row 1 plus row 3. So I go up to the first row. 1 times negative 2 is negative 2 plus 2 is 0. Next entry. Negative 2 times 2 is negative 4 plus, positive 4. Negative 2 times negative 2, positive 4, plus negative 5, negative 1. Negative 2 times 3 is negative 6 plus 5, negative 1. And negative 2 times 9 plus 17, negative 18 plus 17 is negative 1. Okay, well, I'm liking what I see there because now I have a 0 and then a negative 1. But remember, in order for it to be in row echelon form, my leading ones have to be like moving over to the right. So I really can't have a negative 1 or a 1 in the second column of the third row. Can you see an easy way to cancel that out? Add the second row and the third row. Okay, so add the second row to the third row. And again, we're doing it to the third row. So first row, second row, we're leaving alone. 1, negative 2, 3, 9. 0, 1, 3, 5. I'm only changing the third row. And so row 2 plus row 3. That would be 0 plus 0 is 0. 1 plus negative 1, 0. 3 plus negative 1, 2. 5 plus negative 1, 4. Well, I'm getting very close. What would be my last step to get in row echelon form? Change the 2 to 1. Think about your elementary row operations. I probably multiply by a non-zero scalar. What can I multiply by? 1/2. So we're going to multiply row 3 by 1/2. First row, second row stays the same. Be cognizant of that when you're working on homework. Not everything changes in row operations. You should only change one row at a time. Otherwise, you're probably doing too much. Okay. Multiply that whole row by 1/2. We'll get 0, 0, 1, 2. Is that in row echelon form? Yeah. Okay. So you'll have to, on some problems, come up with your own rules. Now, one thing I want to say about this. Why is row echelon form so helpful? Okay. Think back to this augmented matrix at the very beginning. Could you write this as a system of equations? Yeah, something like x minus 2y plus 3z equals 9, so on and so on. Can you change your augmented matrix into a system of equations? Yeah, x minus 2y plus 3z equals 9, y plus 3z equals 5, and 1z equals 2. Is that easy to solve? Yeah, you already know z is 2. You can plug that 2 into that second equation. 3 times 2 is 6. Subtract it, so y is negative 1. And then you can plug negative 1 and 2 in, and that would be plus 2 plus 6, so that's x plus 8 equals 9. Subtract 8, and x is 1. So you're basically like doing the algebra for solving a system, but you're not seeing all those variables because it's organized in a matrix. Cool? Okay, so I want to show you your homework assignment, which is on the gold sheet. The bolded and underlined problems are required. That means you're supposed to do them. I'm going to come around and try to do a better job of checking your homework assignments for completion.